people expected for 40 years before the Higgs was discovered, that the Higgs could not be a lonely elementary particle.
I would like to add my congratulations to everybody involved in this tremendous achievement.
The European Council for Nuclear Research is making groundbreaking discoveries that it is trying to hide from society. Recently, they've unearthed findings so striking from the Large Hadron Collider that they hint at the possibility of alien life in another dimension. This revelation has sparked a global conversation, with experts fiercely debating what this could mean for our understanding of the universe. Could this sensitive information indicate that we are on the verge of understanding phenomena that were once considered beyond our reach? Let's explore the darker, more shocking implications of what lies beyond. The search for new alien particles at European Council for Nuclear Research. At the forefront of scientific exploration, the European Council for Nuclear Research, commonly known as the European Council for Nuclear Research, stands out for its pioneering work in the realm of particle physics. This renowned research hub recently made a startling announcement from its famous Large Hadron Collider, revealing a discovery so unusual that it could radically alter our understanding of the universe. The European Council for Nuclear Research researchers have stumbled upon findings suggesting the possible existence of alien life forms in a parallel dimension. This provocative idea has ignited a wave of excitement and sparked vigorous debates among scientific experts across the globe. It has been a hub of high-risk, high-reward experiments since it was founded in the mid-1950s. It has consistently been in the spotlight, not only for its scientific breakthroughs, but also for stirring public outrage at the European Council for Nuclear Research over potentially dangerous experiments that could create black holes, tear gaps in the fabric of reality, and pose other substantial risks. Among its most notable and debated achievements is the construction of the Large Hadron Collider, the world's largest and most powerful particle accelerator. Operational since September 10, 2008, the Large Hadron Collider is the latest major addition to the European Council for Nuclear Research's complex of accelerators. It features a loop of superconducting magnets that extend over approximately 16 miles and a series of devices that boost the particles' energy levels as they hurtle around the loop. The construction of this colossal scientific instrument cost over $45 billion. However, many argue that the investment has paid off handsomely, as the Large Hadron Collider has led to some of the most important scientific discoveries of recent decades, including detecting the Higgs boson and numerous other particles previously unknown to science. The Large Hadron Collider at the European Council for Nuclear Research is an enormous machine, a marvel of modern science, capable of accelerating subatomic particles to speeds just shy of the speed of light. As these particles zoom around its approximately 16-mile loop, they complete over 11,000 circuits each second, pushed to incredible velocities by a sequence of incredibly strong electromagnets. These magnets create a magnetic field inside the accelerator that is almost 1,000 times stronger than the natural magnetic field surrounding the Earth. There are concerns about the potential impacts of such a powerful magnetic field on the electronics nearby and the Earth's magnetic field itself. As particles within the Large Hadron Collider reach their peak speeds, nearly equal to the speed of light, they are directed to collide with each other head-on. This collision results in a spectacular burst of energy and a spray of new particles, which scatter in all directions. Most of these particles exist only briefly, decaying within fractions of a second. By varying the types of particles that are made to collide, scientists can explore and discover previously unknown particles amid the chaotic aftermath of these collisions. To capture and analyze the results of these particle collisions, the Large Hadron Collider is equipped with highly sophisticated and sensitive detectors placed around the collision sites. These detectors gather vast amounts of data from each collision, precisely recording everything. The data collected is immense, accumulating rapidly and requiring extensive time and resources to sift through. Each year, the experiments at the Large Hadron Collider generate more than 15 petabytes of raw data. The Large Hadron Collider has developed extensive storage systems to manage and store this data. In 2017, a significant achievement was reached when more than 200 petabytes of data were permanently stored in the Large Hadron Collider's tape libraries. To put the volume of this data into context, consider that 1 petabyte alone is equivalent to about 250,000 movies. The sheer scale of data produced by the Large Hadron Collider is staggering, encapsulating a wealth of information that holds the keys to unlocking the mysteries of the universe. This data, when meticulously analyzed, allows researchers to peer deeper into the fabric of reality, testing the limits of our understanding of physics and the universe. In the vast sea of data collected by the Large Hadron Collider, scientists are meticulously searching for clues that could unravel new mysteries of the universe. One particular focus of their investigation is a unique type of subatomic particle known as a quark. Quarks are the very foundation of all matter, existing in several distinct types, or flavors, as physicists like to call them. Each flavor of quark behaves differently, but they are all crucial for forming the protons and neutrons that make up the atoms in everything around us. Among these flavors, some are incredibly unstable, quickly transforming into other types of particles almost immediately after their creation. One such unstable quark is the beauty quark, known for its exceptionally short lifespan, lasting just 1 and 2 trillionths of a second. What caught the scientists' attention was an unusual pattern in how these beauty quarks decay. Typically, according to the standard model of particle physics, when a beauty quark decays, it is influenced by a force known as the weak force and transforms into lighter particles called leptons. The expected outcome is an equal chance of turning into one of 2 types of leptons, either an electron or a muon. However, the recent findings from the Large Hadron Collider have shown something unexpected. The data indicates that when beauty quarks decay, they are turning into muons about 70% of the time, rather than splitting the chances evenly between muons and electrons. This significant deviation from the expected 50-50 split suggests that something unusual is happening, something that the current theories in physics can't fully explain. This anomaly has sparked intense interest and debate among physicists. The observed disparity suggests that a previously unknown particle could influence the decay process, or perhaps it points to a new kind of physical phenomenon entirely. Such a discovery would be groundbreaking, indicating that our current understanding of the fundamental forces and particles might need revising. Researchers are now probing deeper into this data, looking to confirm these findings and understand the implications fully. If this turns out to be true, it could mean the beginning of a new era in physics, with the potential to uncover new forces or particles that could fundamentally alter our understanding of the universe's workings. After a startling discovery, a deeper mystery emerges, suggesting there are forces out there that we've never seen before. Z prime, the particle that will rewrite physics. The discovery of a new force-carrying particle, tentatively named Z prime, could revolutionize our understanding of physics by potentially expanding the current standard model, which is the framework that explains the fundamental forces and particles that make up our universe. This model has been remarkably successful in detailing 3 fundamental forces: electromagnetic, strong, and weak forces, but it doesn't yet account for gravity or explain dark matter, which is thought to make up a significant portion of the universe's mass. The possibility of new physics introduced by Z prime comes from recent observations that didn't align with existing predictions. Such anomalies are not unheard of, given the vast amounts of data generated by experiments like those conducted at the Large Hadron Collider. Still, the specific deviations observed recently have captured the focused interest of the scientific community. These findings suggest the potential existence of a particle that behaves differently than anything we currently understand, interacting in unexpected ways with known particles like electrons and muons. This novel particle could be the key to unlocking many of the universe's long-standing mysteries. For instance, discovering a new fundamental force could shed light on the elusive nature of dark matter and further clarify the role of the Higgs boson in the makeup of the universe. More broadly, it could lead to a more complete and unified theory of physics, which has been a central goal in the field for over a century. The implications of such a discovery are profound, offering answers to complex questions that have puzzled scientists for decades. While the suspected interactions of the Z-prime particle with other standard model particles remain largely speculative at this point, the pursuit of understanding it is a thrilling prospect. It represents a potential paradigm shift in physics, akin to the major breakthroughs of the past, but unique in its promise to bridge gaps in our current theories. The excitement in the scientific community is palpable as researchers around the world work to confirm the existence of Z-prime and explore its implications. If confirmed, this discovery would not only redefine our fundamental understanding of particle physics, but also pave the way for new technologies and insights into the very fabric of the universe. Elon Musk has highlighted that the European Council for Nuclear Research constructed the most enormous and powerful particle collider ever seen in human history, known as the Large Hadron Collider, over a decade from 1998 to 2008. This monumental project was a collaborative effort involving over 10,000 scientists and hundreds of universities, research institutions, and laboratories from more than 100 countries worldwide. The Large Hadron Collider is strategically positioned within a massive, approximately 16-mile-long tunnel that runs beneath the border area between France and Switzerland, close to Geneva, buried about 574 feet beneath the Earth's surface. The construction and operation of the Large Hadron Collider mark a significant milestone in the field of particle physics. It first made headlines when it recorded a collision of protons at an unprecedented energy level of 3.5 tera electron volts per beam, shattering the previous world record by fourfold. Later enhancements to the collider allowed it to reach even greater energy levels, up to 6.5 tera electron volts per beam. These advancements have made the Large Hadron Collider particularly adept at handling proton beam collisions and have equipped it to accelerate lead-ion beams as well. The Large Hadron Collider is not just about achieving high energy levels. It plays a crucial role in scientific experiments. Each year, for about 1 month, the collider conducts specialized collisions between protons and lead ions. This period is critical as scientists use it to test various theories of particle physics, examining the data to validate or challenge existing models. One of the primary objectives of these experiments is to investigate the properties of the Higgs boson, a particle integral to the field theory that explains why other fundamental particles have mass. Moreover, these experiments are essential for probing into the existence of a vast array of new particles that theoretical physicists have predicted but not yet observed. This massive and intricate machine at European Council for Nuclear Research is a cornerstone in the quest to deepen our understanding of the fundamental components of the universe. By smashing particles together at high energies, the Large Hadron Collider allows scientists to peek into the fabric of the universe, offering insights that could potentially answer some of the most profound questions in physics today. The work done here is crucial for advancing our knowledge of the universe and could lead to discoveries that redefine our understanding of everything from the smallest particles to the largest cosmic phenomena. With each discovery, we peel back more layers of the universe, moving closer to uncovering the secrets of the Higgs boson, the dark truth of the God particle. Hadrons are a type of subatomic particle that are composed of smaller particles known as quarks. These quarks are tightly bound together by a force known as the strong force, which is incredibly powerful and acts somewhat like the electromagnetic force that holds atoms and molecules together. Some common examples of hadrons include protons and neutrons, which are the primary components of atomic nuclei. In addition to these, there are other less familiar hadrons, such as pions and kaons, which were first discovered during cosmic ray experiments in the late 1940s and early 1950s. These discoveries have significantly expanded our understanding of the particle world. The Large Hadron Collider at the European Council for Nuclear Research is a remarkable tool in the study of hadrons. It operates by accelerating two beams of particles in opposite directions to nearly the speed of light and then allowing them to collide. These high-energy collisions create an array of different particles, providing physicists a unique opportunity to study the fundamental components of matter. One of the most significant particles studied at the Large Hadron Collider is the Higgs boson. which is believed to be a fundamental particle associated with the Higgs field. The Higgs boson is often compared to ripples spreading across a pond surface. It represents the quantum manifestation of the Higgs field. This field is crucial in physics because it is thought to give particles their mass. The discovery of the Higgs boson was a groundbreaking event in particle physics. It does not carry the properties typical of other quantum particles that mediate forces like the electromagnetic, weak and strong nuclear forces. Instead, the Higgs boson is unique, acting more like a bridge to our understanding of how particles acquire mass. The identification of the Higgs boson at the Large Hadron Collider was a landmark achievement, confirmed through the collaborative efforts of two major experiments, ATLAS and CMS. This discovery was publicly announced on July 4, 2012, marking a significant milestone in the field of particle physics. It validated a key part of the standard model of particle physics, which is the theory that describes the fundamental forces and particles in the universe. This discovery not only deepened our understanding of the structure of matter at the most fundamental level, but also opened new avenues for future research into the origins and composition of the universe. The ongoing studies at the Large Hadron Collider continue to challenge and refine our understanding of the universe, promising even more discoveries in the years to come. At the time, the new scalar boson was discovered primarily in two rare decay channels that provided the purest signal: decay into a pair of photons, which required a totally quantum virtual process, and direct decay into a pair of Z bosons, the carriers of the neutral-weak interaction. Although the finding of the Higgs boson at the time established the standard model, research into this elusive particle did not end there. One of the most significant findings since 2012 was the confirmation of Higgs decay. According to European Council for Nuclear Research, at the time, the research into this elusive particle would deepen during the Large Hadron Collider's third cycle, especially once the particle accelerator's high luminosity upgrade is finished in 2029. This will allow the Large Hadron Collider to undertake more collisions, giving researchers greater opportunity to detect unusual physics, such as occurrences that do not fit into the standard model. European Council for Nuclear Research estimates that when the accelerator is updated, each year it will produce 15 million of these particles. This compares to the Large Hadron Collider's creation of 3 million Higgs bosons in 2017. This might be useful for identifying various flavors of the Higgs boson. Theories that go beyond the standard model of particle physics anticipate up to 5 distinct forms of Higgs bosons, some of which may be created less frequently than the fundamental Higgs. But what's the big deal about the Higgs boson? This Higgs field was incredibly significant and critical in the early times following the universe's creation. It dictates the very nature of the vacuum that exists in our space-time. It is what causes matter and interactions to exist as we know them, as well as the emergence of mass in all known fundamental particles. Without the Higgs field, and consequently the Higgs boson, the cosmos would be devoid of atomic elements, stars, and life. What do you think the Higgs boson is called? The God particle. Popular media helped cement the Higgs boson nickname, the God particle, after its discovery. The genesis of the term is commonly traced to Nobel Prize-winning scientist Leon Lederman, who initially referred to the Higgs boson as the goddamn particle, since it was so difficult to detect. According to Business Insider, when Lederman authored a book about the Higgs boson in the 1990s, he wanted the title, The Goddamn Particle, but the publishers disagreed and changed it to the God Particle. That was the beginning of an issue between the particle and religion that continues to con European Council for Nuclear Research modern physicists. Nonetheless, it is difficult to overestimate the significance of the Higgs boson and the Higgs field, because only particles would have mass under this aspect of nature. That implies there would be no stars, planets, or humans, which may help explain its bombastic nickname. Aside from the apparent need to accurately characterize the new particle, scientists continue to research the Higgs boson for two reasons. First, they want to know how the physical vacuum in which we dwell originated in the early cosmos. Second, they want to know how this physical vacuum can be kept steady. Following the discovery of the Higgs boson, we dive deeper into the quantum world, where big questions about the universe are waiting for answers. Exploring the lost cosmic blueprint. The Higgs field is peculiar in that it transmits non-zero mean anticipated potential energy to the physical vacuum. Essentially, this is what makes all the difference in our cosmos. Scientists think that accessing the form of the energy potential is accountable for the presence of the electromagnetic force with a limitless range and the weak force with extremely little range. To do this, scientists must investigate how the Higgs bosons interact with one another, and for that, they must create pairs of Higgs bosons. The Higgs boson contributed to the answer to the critical question of how all other basic particles get their mass. However, its bulk is yet to be explained. Any symmetry in the theory does not safeguard this mass and causes unintended instability. Quantum fluctuations might disrupt the physical vacuum itself. Fortunately, this is on a timescale much bigger than the universe's known lifespan, but scientists are still seeking for extra Higgs boson-like particles that would indicate the presence of the new physics required to stabilize the Higgs boson mass. All these considerations encourage the study of significantly more data and, if feasible, access to greater collider energy. This is why, 10 years later, hundreds of experts throughout the world remain committed to the effort. The Higgs boson was first proposed in 1964 and found in 2012. Science aficionados have questioned why it took so long. It's because the Higgs boson is both massive and exceedingly unstable. To create such a massive particle, scientists had to concentrate a large quantity of energy in a small container. They required a high-energy collider. Once formed, Higgs particles break apart in a variety of ways, with just a small proportion detectable from the background. Scientists built the largest and most complicated detectors to identify such particles. Then they investigated hundreds of billions of proton-proton collisions to find a Higgs boson signature. However, will the European Council for Nuclear Research's projects and findings enable us to make big discoveries? Will it send us to our ultimate demise? Conspiracy theorists have three main hypotheses about what European Council for Nuclear Research is actually up to. The first and deadliest notion that has caused some to point fingers at European Council for Nuclear Research is that the organization is attempting to open a portal to hell. Some believe that the European Council for Nuclear Research's experiments with subatomic particles flying at the speed of light will carry humanity beyond the gates of the final inferno. However, European Council for Nuclear Research has said that the goal of generating antimatter is to better understand matter and mass. Wikipedia defines antimatter as subatomic particles, having the opposite electrical charge of matter. Supporters of the Big Bang Theory believe that antimatter was formed during the universe's origin and should be represented equally with matter. However, antimatter is extremely uncommon. The second European Council for Nuclear Research conspiracy hypothesis surrounds the Mandela effect. The Mandela effect is a phenomenon in which many people recall a prior event differently than it really occurred. Some conspiracy theorists believe that European Council for Nuclear Research's particle experiments will trigger disruptions in our reality and propel our planet into another realm, resulting in a large-scale Mandela effect. Finally, some conspiracy theorists think that human sacrifice takes place on-site at the European Council for Nuclear Research facility. A video allegedly leaked online in 2016 stating that ritual sacrifices were taking place at European Council for Nuclear Research. The footage purportedly depicted several hooded people going around the European Council for Nuclear Research campus. It was thought that the tape showed a little girl getting stabbed in the chest by the masked people. According to The Guardian, a European Council for Nuclear Research spokesman stepped out to debunk the story, claiming that the ritual was staged as part of an elaborate joke. The question of whether a police inquiry took place after that is yet to be resolved. It is no surprise that European Council for Nuclear Research has long been the focus of conspiracy theories. As a result, it's not surprising that on July 5, 2022, When scientists began operation after 3 years of improvements in maintenance, conspiracy theories would emerge online. While scientific enthusiasts may be disappointed with this revelation, it is apparent that European Council for Nuclear Research has no ambitions to build a doorway to hell, the future, or any other dimension. As we reflect on the European Council for Nuclear Research's past discoveries, we prepare to explore how ghost particles might shed light on the universe's darkest mysteries. The hunt for neutrinos, elusive ghosts. Ghost particles, or neutrinos, have been detected for the first time by a particle collider, thanks to the Large Hadron Collider, the world's biggest particle accelerator. This remarkable machine, which stretches a massive 17 miles and sits more than 300 feet underground, has been smashing tiny particles together at incredibly high energies for nearly 10 years. These high-energy collisions allow scientists to explore new areas of physics, areas we've never seen before. Recently, a special part of the Large Hadron Collider called the Forward Search Experiment Detector made a surprising discovery. It found 153 high-energy neutrinos with amazing precision. This is a huge deal in the world of particle physics because it could help scientists understand some really intense processes in the universe better, like how stars explode into supernova. The Large Hadron Collider isn't just about looking for new particles, it's also been central to some major breakthroughs in physics. For example, a few years ago, scientists at the European Council for Nuclear Research discovered the Higgs boson, a particle that's a big part of why things have mass. The recent detection of neutrinos is another milestone that pushes the limits of what we know about the universe. But not everyone sees European Council for Nuclear Research's work as purely scientific. Some people have come up with theories that the experiments could lead to disasters or that there are secret, evil plans behind them. However, these ideas don't really hold up when you look at the facts. Experts have debunked these theories, reassuring the public that the work being done is safe and important for our understanding of the universe. In reality, European Council for Nuclear Research remains dedicated to advancing scientific understanding for the betterment of humanity. Its experiments not only expand our knowledge of the universe, but also drive technological innovation and inspire future generations of scientists. As we look to the future, the discoveries yet to come from European Council for Nuclear Research promise to further revolutionize our understanding of the cosmos. Whether unraveling the mysteries of dark matter, exploring the nature of space-time, or probing the fundamental forces of the universe, European Council for Nuclear Research continues to lead humanity on a journey of discovery and enlightenment. So, as we eagerly anticipate the next chapter in European Council for Nuclear Research's scientific endeavors, let us celebrate the organization's remarkable achievements and the profound impact they have had on our understanding of the universe. And who knows what groundbreaking discoveries await us as we venture deeper into the mysteries of the cosmos with European Council for Nuclear Research at the forefront of scientific exploration. As we stand on the cusp of unprecedented discoveries, it's a reminder of the beauty of human curiosity and the power of collaboration on a global scale. With each experiment conducted at European Council for Nuclear Research, we inch closer to unlocking the secrets of the universe and gaining deeper insights into the nature of reality itself. The intricate dance of particles within the Large Hadron Collider and the meticulous analysis of data by researchers pave the way for groundbreaking revelations that have the potential to reshape our understanding of the cosmos. European Council for Nuclear Research embodies the spirit of exploration and serves as a powerful source of inspiration for people all over the world who are interested in science. This includes scientists, teachers, and anyone else who's simply curious about how the universe works. European Council for Nuclear Research reminds us how important it is to keep asking questions and searching for new knowledge, not just for the sake of discovery, but to make the world a better place. Standing together with European Council for Nuclear Research, we are at the beginning of a new era of discovery, where what we know about science and the limits of our imagination come together to shed light on the universe in ways we've never imagined before. Neutrinos, often called ghost particles, are incredibly small particles that are almost everywhere around us. But they are very hard to detect because they rarely interact with other matter. These particles are created in several ways. When the nuclei of atoms come together or split apart, through the process of radioactive decay, by cosmic rays hitting the Earth, and even in the operation of particle accelerators and nuclear reactors. Interestingly, everyday items like bananas, which contain a bit of natural radioactive potassium, also produce neutrinos. However, these massless and chargeless particles represent the ultimate cosmic ghost. Once created, they seldom interact with matter. Every second, around 100 billion neutrinos travel through each square centimeter of our bodies, but they are so elusive that we cannot feel them. This mysterious characteristic gave them the nickname ghost particles, and scientists have been hunting them since 1956, when they were first detected zipping from a nuclear reactor. Physicists at European Council for Nuclear Research made an exciting discovery in 2021 when they detected traces of 6 neutrinos. However, proving that these traces were indeed real took 2 years of meticulous data collection and analysis. James Boyd, a notable particle physicist at European Council for Nuclear Research and co-spokesperson for the FAIR project, highlighted the unique value of these ghost particles. He explained that these high-energy neutrinos provide insights into the depths of space in ways that no other methods can. This is particularly true at the Large Hadron Collider, where these neutrinos play a crucial role in unraveling complex astrophysics phenomena. The Large Hadron Collider project is set to continue its operations and data collection through the end of 2025. During this period, scientists are hopeful that they will detect more of these ghost neutrinos. Each new discovery of a neutrino brings us closer to solving some of the biggest mysteries in physics that we have yet to fully explore. The anticipation is palpable among the scientific community, as each finding could potentially open new avenues of understanding in particle physics and cosmology. Everyone is eagerly waiting to see what European Council for Nuclear Research will reveal next, and how these discoveries will shape the future of scientific exploration and our understanding of the universe. Could this discovery at European Council for Nuclear Research reveal more than just new science, possibly even secrets about our universe? Share your thoughts, and don't forget to like and subscribe for more insights.